Hi guys, this is the EdExcel A-Level Further Maths Paper 3 from the June 2019 series, and in this video we'll be taking a look at the Decision 1 module. Examiner report wise, overall the paper proved accessible to most candidates, which is good, but there were a significant number of candidates who struggled to cope with the new content not previously seen in the legacy modules D1 and D2. Some had difficulty with the problem-solving nature of some of the questions. And in terms of this paper, when we talk about D1 and D2, you're reminded that this is a methods-based examination. So show your method clearly. Obviously, spotting the correct answer with no working rarely gains any credit. The space provided in the answer book and the marks allotted to each section should assist candidates in determining the amount of working they need to show. Some very poorly presented work was seen, and some of the writing, particularly numbers, was very difficult to decipher. And we're also told that candidates are reminded that they should not use methods of presentation that depend on colour, but are advised to complete diagrams in dark pencil. I know in this video I will be going through my solutions in colours to make it easy for everybody to understand, but just as a reminder, in the exam you have to use dark pencil. A lot of candidates used highlighters, even though that's not allowed as well. So this sort of pen should not be used. Okay, so for question number 1, we have to use the first fit bin packing algorithm to determine how the numbers listed above can be packed into bins of size 5. So for this question, the way I like to do questions like this is the following way. For part A, first of all, label your first bin number 1. Okay? Now, if you remember from the question, we were told that we have a bin size of 5. Okay, so let's just rule off down here somewhere. And we work in the order that's given. We start off with 2.1. 5 take away 2.1, that's 2.9. So now we've got a capacity of 2.9 remaining. Let's cross off the 2.1, indicating we've used it. Next, look at the 1.7. Can the 1.7 fit into this first bin? Yes, because we've got 2.9 left over. So we write down 1.7. and 2.9 take away 1.7, that's 1.2. Okay, let's cross off the 1.7, indicating we've finished with the 1.7. Now we look at the 3. Can the 3 fit into this first bin? It can't, because we've only got a capacity of 1.2 remaining, so we have to go to a new bin. Obviously we started off with a capacity of 5. 5 take away 3.0, that's 2. Okay, now we look at this 1.9. Can the 1.9 fit into the first bin? It can't, because we've only got a capacity of 1.2 remaining. Whereas if you look at the second bin, we've got a capacity of 2 remaining. So we can fit this 1.9 into the second bin. So what will be left over is 2 take away 1.9, which is 0.1. So that's the 1.9 done. Next, look at the 3.2. We can't fit it into the first bin, we've only got 1.2 remaining. We can't fit it into the second bin, we've only got 0.1 remaining. We have to start a new bin. So we write down 3.2. Initially, we have 5 take away 3.2, That's 1.8. Okay, so let's cross off the 3.2, indicating we've finished with the 3.2. Let's now look at the 1.2. The 1.2 can fit into the first bin because we've got a capacity of 1.2. So we write down 1.2 here, and let's cross off this 1.2, indicating we've finished with the 1.2. Let's now look at the 3.3. It can't fit into the first bin, we've got 0 capacity left. It can't fit into the second bin, we've only got a capacity of 0.1. It can't fit into the third bin, we've only got a capacity of 1.8. We have to start a new bin, and we write down the 3.3. Initially we start off with 5 take away 3.3, that's 1.7. So now we cross off the 3.3, indicating we've finished with the 3.3. Let's now look at this 1.4. It can't fit into the first bin, we've got a capacity of 0. It can't fit into the second bin, we've got a capacity of 0.1. Whereas for the third bin, we've got a capacity of 1.8. 1.4 definitely does fit into here. And 1.8 take away 1.4, that's 0.4. Okay, so let's cross off the 1.4, indicating we've finished with the 1.4. Let's now look at this 1.5. It can't fit into the first bin, we've got a capacity of 0. It can't fit into the second bin, we've got a capacity of 0.1. For the third bin, we've got a capacity of 0.4, so it can't fit into the third bin. But the fourth bin, that's got a capacity of 1.7. 1.5 goes into 1.7, so we write down 1.5 here, and then we've got 0.2 left over. Let's cross off this 1.5, indicating we've done with the 1.5. Now let's look at this 0.2. It can't go into the first bin, we've got capacity of 0. It can't go into the second bin, we've got capacity of 0.1. But the third bin, we've got a capacity of 0.4, 0.2 fits into here. So we write down 0.2 here, and what's left over is 0.2. So this over here is our completed bin, as shown. Okay. For part B, the list of numbers is now to be sorted into descending order. We have to perform a quick sort on the original list. To obtain the sorted list, you should show the result of each pass and identify your pivots clearly. The key in this question, we have to sort the numbers in descending order. So what I've done so far, I've listed out the numbers exactly as they appear over here, and I think there's a spare set in the answer book. The first thing we need to do is identify our pivot. Now, there are 10 numbers here, and for our pivot, because 10 is an even number, we divide 10 by 2, which gives us 5, and then we add 1, which is 6. So we want to find the 6th number. The 6th number is this 1.2 here. So then we put a box around it, indicating this is our pivot. We then compare all these numbers with the 1.2. Anything that's bigger than the 1.2, we write to the left. Anything that's smaller than the 1.2, we write to the right of the 1.2. So 2.1, that's bigger than 1.2. 1.7, that's bigger than 1.2. 3.0, that's bigger than 1.2. 1.9, that's bigger than 1.2. 3.2, that's bigger than 1.2. 3.3, that's bigger than 1.2. 1.4, that's bigger than 1.2. 1.5, that's bigger than 1.2. the 0.2 that's smaller than the 1.2. So we write the 1.2 to the right. So we have 1.2 here and then the 0.2 here. And then you simply underline the 1.2, indicating that you've already chosen it as a pivot. Now, if you look at these 8 numbers here, the pivot is the middle number, which we find by dividing 8 by 2 and then adding 1. So 8 divided by 2, that's 4, plus 1, that's 5. So we want the fifth number. The fifth number you'd find to be 3.2. We put a box around that, indicating this is our pivot, and then we compare these numbers with the 3.2. Anything bigger than 3.2, we write to the left. Anything smaller than 3.2, we write to the right. So 2.1, 1.7, 3.0, 1.9, they're all smaller than 3.2. Whereas the 3.3, that's bigger than the 3.2, so we write 3.3 here, and the 1.4, the 1.5, the 1.2, and the 0.2 are all smaller than the 3.2. So the 3.2 goes here. Remember to underline, indicating this is your pivot, and then we write the rest of the numbers as they remain. So we have 2.1, 1.7, 3.0, 1.9, 1.4, 1.5, 1.2, and 0.9. Do also remember to underline the 1.2, indicating you've already chosen it as a pivot. And if you now look at the remaining numbers here, we've got 1, 2, 3, 4, 5, 6 numbers. Half of 6, that's 3, plus 1, that's 4. So we want the fourth number in this sublist, 1, 2, 3, 4. That corresponds to the 1.9. We put a box around the 1.9, indicating that's our new pivot. And then we compare these numbers with the 1.9. We've still got this 3.3, this 3.2. Remember 3.2s, we've already used it as a pivot. So in terms of what's bigger than the 1.9, 2.1, that's bigger than 1.9. 1.7, that's smaller than 1.9, but the 3.0, that's bigger than the 1.9. So 3.0 goes here, and then we have the 1.9 here. Okay, let's underline the 1.9, indicating this is used as a pivot, and then we've got the 1.7, and then we've got the rest of the numbers, the 1.4, the 1.5, the 1.2, and the 0.2. Underline the 1.2, indicating that you've used it as a pivot. And if you look at this sublist here with the 2.1 and the 3.0, we've got two numbers here, so the middle value is half of the 2, which is 1, plus 1, which is 2, so we want the second number, which is 3.0. We put a box around the 3.0, indicating that's our pivot. And if you also look over here, we have 3 numbers. The middle one, that's nice and easy. That's just the 1.4. So what do we do? Right, comparing these two, 2.1 is smaller than 3.0. So the 3.0 goes here, and then the 2.1 goes there. Remember to underline the 3.0, indicating that you've used it as a pivot. And we've also got the 3.3 here and the 3.2 here. Okay, so now we look at the numbers here. if we compare the 1.7 with 1.4, you'd find 1.7 is bigger than 1.4, so that remains here. So we have 1.7 here. We still have this 1.9 that was used as a pivot. Then we've got this 1.4 and the 1.5. The 1.5 is bigger than 1.4, so we swap those and the 1.4 goes here. Don't forget to underline the 1.4, indicating that has been used as a pivot. Then we've got this 1.2 and this 0.2 here. Underline the 1.2, indicating you've used it as a pivot. Now, for these sublists, if we have one entry in the sublist, we can stop. But here you'd find there's two entries in the sublist, so the middle one, half of 2 is 1 plus the 1, that's that's 2, so we want to choose the second number, which is the 1.5. So we compare the 1.7 with the 1.5, the 1.7 is bigger, so that can remain there as it is. And we've got this 1.5. Underline the 1.5, indicating that you've used it as a pivot. And then we've got the rest of the numbers. We've got the 3.3, the 3.2, the 3.0, the 2.1, the 1.9, the 1.4, the 1.2, and the 0.2. And let's indicate what we've used as a pivot. We've used the 3.2, the 3.0, the 1.9, the 1.4, and the 1.2. Okay? And now, because there's one entry in each of the sublists, we can stop. Okay? So that's the end of the quicksort. For part C, for a list of n numbers, the quicksort algorithm has on average order n log n, and given that it takes 2.32 seconds to run the algorithm when n equals 450, we have to calculate approximately how long it will take to the nearest tenth of a second to run the algorithm when n equals 11,250. You should make your method and working clearly. Okay. So for part C, we want to find how long it will take when, if you go back to the question, we want to find how long it will take to the nearest tenth of a second. I think that's actually quite important. How long the algorithm will take when n equals 11,250. So we've got this 2.32, and then we multiply this by fm over fn. So fm, that will be 11250 times by the log of 11250, and then fn, that is 450 log 450. So if we work this out, let's grab our calculator. We have 2.32 times by 11250 times by the log of 11250, and then here we have 11250 times by the log of, sorry, we have here 450 times by the log of 450. It turns out we get 88.55937664. But remember, the question said to the nearest tenth of a second, so we have 88.6 seconds. Okay. Examiner report wise for question 1. For part A, we had to use the first fit bin algorithm. A lot of candidates struggled in applying first fit bin algorithm correctly. First fit is just that. Candidates must decide if the current item under consideration will fit in the first bin rather than the most recent bin used. The next point is quite interesting. Several candidates placed the 1.2 in the third bin and not the first bin. I think because there was some space left, that's why they put it in the third bin rather than the first bin, which is incorrect. In terms of part B, where we had to use the quicksort, putting our numbers into descending order, there were a lot of correct solutions, but there were several candidates who did not choose their pivots consistently, switching between middle left and middle right pivots during the quicksort algorithm. Several candidates either lost an item or changed an item during the sort, and in a small number of cases only one pivot was chosen per iteration, and I think in some of the iterations we could choose two pivots, like over here. As stated in previous examiners' reports, candidates must make it clear that the sort is complete by either explicitly stating that the sort is complete, or by choosing each item as a pivot, or by rewriting the final list. That's actually quite important, so pay attention for that. You're given some further advice. Candidates should be reminded that items should remain in the order from the previous pass as they move into sublists. We've got more advice and comments given. Pivots were usually chosen consistently, although the spacing and notation on some solutions made these difficult for the examiners to follow. I think boxing the pivots helps quite a lot, and underlining what you've already chosen as a pivot helps a lot as well. There were some candidates answer in ascending order and then remembered to reverse their list at the end, and they gained full credit. But there were some who left their list in ascending order. For part C, where we had to look at the efficiency of the algorithm, that was done quite well, but there was some that said something about the nearest tenth of a second, and some candidates did not put their answer to the nearest tenth of a second. Question number 2. We have figure 1 over here, which represents a network of corridors in a building. The number on each arc represents the length in meters of the corresponding corridor, and the total weight of the network is 370. For part A, we have to use Dijkstra's algorithm to find the shortest path from A to D, stating the path and its length. So we want to start at A and finish at D. Okay. So you'll notice in terms of the box, we've got the vertex, we've got the order of labeling, we've got the final value, and then we've got the working values, which goes at the bottom box. Now we want to start at A, so let's label this. We want to start at A, so we have a 0 that we start off with, and we carry that through into our final value box, so we have 0 in here, and then the order of labeling, we assign A with the number 1. 0 plus 75, that's 75. 0 plus 42, you'd find that to be 42. And 0 plus 38, that would be 38. The smallest value, you'd find that to be the 38, so we carry the 38 into the final value box, and then we assign B with the number 2. we continue working like this. So 38 plus 42, you'd find that to be 80. 38 plus 15, you'd find that to be 53. And out of these values, you'd find the 42 to be the smallest, so we carry the 42 into this final value box and we assign f with a number 3. We continue as normal. 42 plus 20, you'd find that to be 62. 42 plus 12, you'd find that to be 54. 42 plus 39, you'd find that to be 81. Okay? And the smallest value out of all of these, you'd find that to be this 53. In the final value box, we write a 53 and we assign E with a number 4. We continue as normal. 53 plus 10, that's 63. However, the 54, that's smaller than the 63, so we leave out the 63. Perhaps if we write the 63 in brackets, that might help. 53 plus 17, that would be 70. And there are no other values to put in. And out of all of these, the next smallest one is the 54. So we put the 54 into the final value box and we assign G with a number 5. Okay? Let's continue as normal. 54 plus 23, that would be 77. 54 plus 14, that would be 68. And that's all. The next smallest one, you'd find that to be this 54 plus 7, which is 61. So we put 61 into the final value box and we assign C with the number 6. Okay. Now we've got these 3 boxes left. So the next smallest one, that would be the 68. So we carry the 68 into the final value box. We assign J with the number 7. And then 68 plus 6, that would be 74. And then 68 plus 10, that would be 78. You'd find over here the smallest value now, that would be the 74, so we put 74 into the final value box and then we assign H with the number 8. Okay? And the last value, that would be the 78. We assign D with the number 9. Okay? So, in terms of the shortest path from A to D, the shortest path we can work out by working backwards. Okay? So, if we work backwards, obviously we finish at D, and then 78 take away 10 is 68, so then we go down to H, and then from J we can do 68 take away 14, which is 54. That takes us to G. Then from G we can do 54 take away 12, which is 42. So that takes us up to F. And then from F, 42 take away 42, that's 0. That takes us back to A. So in terms of the shortest path, we have A, F, G, J, D. Okay, so this here is our shortest path, and the length of this shortest path, we found that to be the 78 as shown here. Now for part B of the question, on a particular day, NASA needs to check the paintwork along each corridor. NASA must find a route of minimum length. It must traverse each corridor at least once, starting at B and finishing at G. We have to use an appropriate algorithm to find the arcs that will need to be traversed twice. You must make your method and working clear. Okay, so the first thing I recommend that everyone does for part B is to label the order of the vertices. Okay, so we'll do this in orange. A, that has order 3, B, that has order 3, D, that has order 2, C, that has order 3, E has order 3, F has order 4, H has order 3, J has order 4, and G has order 5. And what you'd find over here, the vertices with odd order, that's 3, the 3 here for B, the 3 for E, the 3 for C, the 5 for G, and the 3 for H. So let's write that down. The odd vertices, you'd find them to be B, G, A, C, E, and H. And we were told in the question that we want to start at B. Okay, so we want to start at B, and then we want to finish at G. And because we have more than 4 odd nodes, we know that B and G, we're starting at B, we're finishing at G, and therefore B and G must remain odd. Let's write that down. So B and G must remain odd. Okay. And we've got 4 vertices left, and what we do with them is we find the odd pairings with these vertices. So we will now find the odd pairings from A, C, E, and H. So let's pair these together. We've got A and C plus E and H, and then we've got A and E plus C and H, and then we've got A and H, and then C and E. Now, with these, if you think about AC, we want to start at A and finish at C. The way we can go to C via the shortest way, we can't go from A to C directly because that has a length of 75. Whereas if we start at A, go to F, then go to G, then go to C from that, we have 42 plus 12 plus 7, which is smaller than the 75. So AC, we can readjust that to give us A, F, G, C. And then EH, starting at E, finishing at H. So EH, the smallest root, we can go from E to J and then to H. So EH, that's E, J and H. For AE, if you think about A and then finish at E, the way we can go to E from A is via B, that's the shortest route. So we have A, B, E for AE. So we have A, B, E. And then for CH, starting at C, finishing at H, we can go from C to G, and then from G we can go to J, and then from J we can go to H. So we have C, G, J, H. And A to H, starting at A, finishing at H, we can go from A to F, F to G, G to J, and then J to H. So just be careful of the different routes you can take to go from A to H. The route I just said, which is A, F, G, J, H, that's the shortest way. And then CE, we can get to E from C via G. So we have C, G, E. So we have C, G, E. And if we work out these lengths, so AFGC, if we work that out, AFGC, we have 42 plus 12 plus the 7, that's 61. And then E to J, so E to J, that's 17, and then plus the 6, that's 23. You'd find this to be 84. And then ABE, so ABE, that's 38 plus 15, which is 53. And then C to G, that's 7 plus the 14 plus the 6, that's 27. Adding these together, we get 80. And then A to F, 42 plus FG, which is 12, plus the 14, and then plus the 6, that's 74. And then CGE, so we have 10 plus the 7, which is 17. And adding these together, we get 91. Okay? And what you'd find over here then is here we have the smallest value, and therefore we'd have to repeat AB, BE, CG, GJ, and JH. Okay? So those are the, if you go back to the question, those are the arcs which need to be traversed twice. And now for part C, we have to find the length of Nas's route. So the length of his route, well, we have the 370, which is, if you go back, that's the weight of the total network. So for part C, the length of the route that would be the 370 plus this 80, which is 450 meters. Okay. And now for part D. On a different day, all the corridors that start or finish at B are closed for redecorating. NASA needs to check all the remaining corridors and may now need to start at any vertex and finish at any vertex. A route is required that excludes all those corridors that start or finish at B, and we have to determine the possible starting and finishing points so that the length of NASA's route is minimized. You must give reasons for your answer, and then we have to find the length of NASA's new route. Well, if we go back here, if we can no longer go to B and all those arcs are crossed out, we can't go along here, we can't go along here, and we can't go along here. And therefore, the orders of the vertices now become 2. So we got 1, 2. F, that still remains as 4. H, that remains as 3. J, that remains as 4. D, that now remains as 1. E, that changes to 2. And C, we've still got 3. And G, we've still got 5. Okay, so what we can now say is that, and we'll write this down in a different colour, if B is removed, then D, C, G and H are now odd. Okay? And now the weight with B removed, so the weight with B removed, well, we've got this 370, we have to now subtract off the 38, the 15 and the 42. So we have 370 take away 38, take away 42, take away 15. You'd find that to be 275. And with these remaining vertices, the shortest path between any two nodes, if you go back, that would be CG, which of course is 7. So let's just write that down. The shortest path between any two nodes that would be CG, which has a length of 7. And so if you think about this, the odd nodes, the D, the C, the G and the H, what we can say from here, and if I write this down in a different colour, because the shortest path between any two nodes is CG, we would have to repeat CG. Okay? And therefore, if we repeat CG, we can therefore conclude that we can start or finish at we can start and finish at D or H, and we can repeat CG. Okay, and then the length of the new route we have the 275 plus the 7 from CG, which is 282 meters. Okay. Examiner report wise for question number 2, for part A we had to use Dijkstra's algorithm, A lot of candidates were well prepared for this type of question, and there were just slight slips which didn't show a lack of understanding. There were just small little errors. There were the standard errors in the order of working values and or extra or missing values, and examiners saw several cases where there was no replacement of working values whatsoever. As is often the case, handwriting presented something of a challenge when deciphering working values. Candidates should be reminded of the importance of working values in judging the application of the method by examiners, and so candidates should ensure that their presentation is clear, and it cannot be stressed enough that working values should not be crossed out. And if you actually have a look, you've actually got plenty of space to put other working values as well. Just put a comma next to them. For part B, I think this one was, well, part B and C, that was using the Chinese postman algorithm. A lot of candidates were able to identify the correct 4 odd nodes, and most paired them correctly, which is good, and there were other slight mistakes made. Candidates should, however, note the requirement for repeated arcs rather than repeated pairings, as there were several candidates who lost a mark for stating simply AE plus CH. Some candidates were clearly on autopilot and stated the length of the route here rather than or as well as in part C. For part D, where that was basically an application of the Chinese postman, that was quite a testing question. Those who did attempt this part of the question, they were limited to the mark for identifying which nodes were now odd, and some candidates got stuck after finding there were 3 or 5 odd nodes. Some candidates who had identified the 4 odd nodes seemed unsure how to proceed, giving unjustified start and finish points and ignoring the arc that needed to be replaced. A small but worrying number of candidates persisted in using the avoid the longest of the repeats misconception, but there were other general mistakes which you can also read about. Okay, so for now, question number 3. We've got the network in figure 2 over here, which shows the direct roads linking 5 villages A, B, C, D and E. The number on each arc represents the length in miles of the corresponding roads. The roads from A to E and from C to B are one way, as indicated by the arrows. For part A, we have to complete the initial distance and route tables for the network provided in the answer book, and that's worth 2 marks. So in terms of our initial tables, obviously we can't go from A to A. In a similar way, we can't go from B to B, C to C, D to D, and E to E. And the way we fill the initial route table, we look down the columns and then we copy the letter corresponding to those columns. So down column A, we have all A's. For column B, we have all B's. For column C, we have all C's. For column D, we have all D's. And for column E, we have all E's, as shown. Now, in terms of the numbers, if you think about A to B, start at A and finish at B, that's 15. Okay, and A to C, if we go back, start at A, finish at C, that's 7. So let's just add that in, we have 7 here. A to D, start at A, finish at D, you'd find that to be 18. So let's just fill that in, we have 18 over here. And A to E, start at A, finish at E, that would be 3. So let's just fill that in. We have 3 over here. But if we start at E and finish at A, there's no direct way of doing that. Notice we have the one-way arrow from A to E, and therefore we would fill EA with an infinity. Now, in terms of B to A, start at B, finish at A, that also is 15. And B to C, start at B, finish at C, well, there's no direct way we can go from B to C, therefore we write down an infinity. So we have infinity here. B to D, if you go back to the table, start at B, finish at D, there's no one direct path we can take, and therefore we fill that in with an infinity. And B to E, start at B, finish at E, there's no direct way we can go from B to E, and therefore we fill that in with an infinity. Now, C to A, start at C, finish at A, that's 7, so we have 7 over here. CB, start at C, finish at B, that would be 5, we can fill that in, no problem. C to D, start at D, finish at C, so C, D, that would be 4, so we have 4 over here. And CE, start at C, finish at E, that would be 9, so we can fill this in with a 9. Start at D, finish at A, can we do that? If you go back to the table, start at D, finish at A, that would be 18, so we have 18 over here. D to B, start at D, finish at B, there's no one way we can go from D to B, and therefore we fill that in with an infinity. Start at D, finish at C, so start at D, finish at C, that would be 4. Start at D, finish at D, obviously we fill that in with a blank. Start at D, finish at E, so DE, that would be 3. E to B, start at E, finish at B, no direct way of doing that, so we have an infinity here. E to C, start at E, finish at C, well, we can do that, that would be 9, so we have 9 here. And E to D, start at E, finish at D, that would be 3. So here we have completed our initial distance table and our initial route table. And for part B, we have to perform the first 3 iterations of Floyd's algorithm. You should show the distance table and the route table after each of the 3 iterations. Now, the way we approach this question is we start off looking at A. Perhaps if you highlight that, we will look at this A to begin with and highlight the corresponding entries in the initial route table. Now, what we have highlighted, that will remain the same for our first iteration. That's quite important. So for our first iteration, whatever I've highlighted remains the same. So we have a dash, a 15, a 7, an 18, an infinity, a 15, a 7, an 18, and a 3. And the letters also remain the same. We have A's going all the way down like so, and then we have B, C, D, and E. Now, these will also remain the same, so will the corresponding letters. So here we have B, C, D, and E. Okay, now what we do is we look at the entries remaining and we compare those to the values highlighted. So for example, for BC, we compare the infinity with 15 plus 7. 15 plus 7 is smaller than this infinity, and therefore we have 22 over here. We've replaced the infinity with 22, so we circle it. And for the root table, we're looking at A, and therefore we write down an A over here and circle it, indicating you've changed. Okay? Now, for BD, start at B, finish at D, we compare this infinity with 15 plus 18. 15 plus 18, that's 33. So we have 33 over here. We circle it because we've replaced the infinity with 33. The letter will also change from D to A. For this element, we compare the infinity with 15 plus 3. 15 plus 3, that's 18, which is smaller than infinity. So we replace the infinity with 18, and we replace the E with an A. For CB, we compare the 5 with 7 plus 15. 7 plus 15, that's 22, which is bigger than the 5, so we don't make any replacements. So we have the 5 here, and we still have the B over here. Let's now look at CD. We have the 4. We compare that with 7 plus 18. 7 plus 18, that's bigger than the 4. So we have the 4 over here, which remains unchanged. The letter will also remain unchanged. We have D over here. For CE, we compare the 9 with 7 plus 3. 9 is smaller than 10, so we write down the 9 over here. We've not changed anything, so this will remain as an E. For DB, start at D, finish at B, we compare the infinity with 18 plus 33. 18 plus 15, that's 33. That's smaller than infinity, so we replace the infinity with 33. And because we've replaced the infinity with 33, we also replace the letter to an A, as highlighted. For this element, we compare the 4 with the 18 plus 7. 4 is the smaller one, so that remains unchanged. The letter will also remain unchanged. For DE, we compare the 3 with 18 plus 3. 21 is bigger than the 3, so we make no changes. Okay? Now, for EB, we compare the infinity with infinity plus 15. So, infinity plus 15 is bigger than infinity, so we make no replacements. Here we still have the B. Next, we compare the 9 with infinity plus 7. 9 is smaller, so we don't make any replacements. Okay? Now, for the final one, we compare the 3 with infinity plus 18. 3 is definitely smaller. Again, we make no replacements. So we have 3 and D in our distance and root tables. So that's our first iteration done. Let's now move on to our second iteration. So, for our second iteration, this time, instead of looking down A and across A, we look down B and across B. Obviously, we highlight those in the distance and root tables, and whatever I've highlighted remains the same. So we have 15, a dash, a 5, a 33, and an infinity, a 15, a 22, a 33, and an 18 here. And then here we have A, B, A, A, A. Here we have B, B, A, Okay, so having made these replacements, here we would also have blank entries. We copy those out as well. So we have A, the B is already filled in, then we have C, D and E. And we do the same thing that we did with our first iteration. So we could, if we look at AC, we compared the 7 with the 15 plus 22. The 7's obviously smaller, so the 7 remains unchanged. The letter also remains unchanged. Okay? And we then compare the 18 with 15 plus 33. The 18's smaller. Again, we make no adjustments. We then compare the 3 with 15 plus 18. The 3 is definitely smaller. We make no adjustments. If we take a look at CA, start at C, finish at A, we look at the 7, we compare that with 15 plus 5. The 7's smaller. We make no adjustments. We now compare the 4 with 5 plus 33. 4 is definitely smaller. Again, we make no adjustments. And then we look at the 9, we compare that with 5 plus 18. 9 is smaller. We make no changes. Now, we compare the 18 with 15 plus 33. The 18 is smaller. We make no adjustments. We now compare the 4 with the 33 plus the 22. The 4 is definitely smaller. We make no adjustments. And over here we compare the 3 with the 33 plus 18. 3 is definitely smaller. We make no adjustments. Here we compare the infinity with 15 plus infinity. 15 plus infinity, that's bigger than the infinity. We make no adjustments. Now we look at the 9, we compare that with infinity plus 22. 9 is smaller. We make no adjustments. We now compare the 3 with infinity plus 33. 3 is smaller. We make no adjustments. So let's just check our second iteration. We have A, B, C, D, E, A, B, A, A, B, C, D, E, A, C, D, E, and A, B, C, D, E. So nothing has changed. Now for our third iteration, we've looked down A, that was in the first iteration. We've looked down B, that was in the second iteration. Now we look down C for the third iteration. So we highlight to keep a track on what we're comparing with. Remember to highlight again with the root table, like so. Those remain the same, so let's just copy those out as they are. So we have 7, 22, blank 4, 9, 7, 5, 4, 9. Then we have A, B, C, D, E, C, A, then C, C, C. Okay, and we also have blanks over here. We have A, B, C, D, and E as shown. Okay, so what we do is the same thing as we did in the first and second iterations. Here we compare the 15 with 7 plus 5. 15 is smaller, we make no changes, so we have 15 and B. Okay. Let's just double check that. Sorry, we do make a change, rather. 15 is smaller than the 12, so we do make a change. We put a 12 over here. We circle it to indicate we've changed. And then, because we're looking down the C column and row, we replace the B with a C, and we circle it to indicate we've changed. Okay. Next, we compare the 18 with 7 plus 4. 7 plus 4, that's 11. That's smaller than the 18. We've made a change, so circle, and we replace the D with a C. Circle it. Next, we compare the 3 with 7 plus 9. 3 is the smaller one. We make no changes. Now for BA, we compare the 15 with 7 plus 22. 15 is definitely smaller. We don't have to make any changes. Now for this element here, we compare the 33 with 22 plus 4. That's 26. 26 is definitely smaller. Put a circle around it indicating we've changed. And then here we have a C. Okay. And for this element, we compare the 18 with 22 plus 9. 18 is definitely smaller. We don't have to make any changes whatsoever. Okay. Now, we compare the 18 with 7 plus 4. That's 11. 11 is smaller than the 18. So we have 11. We circle it to show we've changed. And then we have a C over here. Okay, now we compare the 33 with 5 plus 4, that's 9. The 9 is definitely smaller, circle it to show that you've changed. We have a C over here. And over here we compare the 3 with 4 plus 9. 3 is definitely smaller, we've made no changes. Next, we compare the infinity with 7 plus 9. So we have 16, which is smaller than infinity. Circle it to show that we've changed, and we replace the A with the C. Next, compare the infinity with 5 plus 9. 5 plus 9, that's 14. 14 is definitely smaller, and then we replace the B with the C. Circle them to show that you've changed. Next, we compare the 3 with the 4 plus the 9. 3 is definitely smaller, we can make no changes. So we have our third iteration complete. For the first row, we have A, C, 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 E. For the second row, we have A, B, A, C, A. For the third row, we have A, B, C, D, E. Then for D and D, we have the same thing, C, 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 D, E. Okay, so that over here is part A and part B done. Okay, so now for part C, after 5 iterations of Floyd's algorithm, the final distance table and partially completed final root table are shown below. For the first part of part C, we have to explain how the partially completed final root table can be used to find the shortest route from E to A. Okay, now for this question, what we essentially do is we want to start at E and finish at A. And if you look at that, we want to start at E and finish at A. And you'll notice we have a D over here. So we first of all have to go to D to get to A. So now that we're at D, if you look, we want to go from D to A, and you'll notice there's a C in the way. So from D we have to go to C. So now that we're at C, can we go to A from C? Yes, we can, because there's an A over here which takes us up to C. And in terms of the route then, the route we'd have is E, then the D, then the C, and then the A. That's our route. So when we come to talk about, when we come to explain how the partially completed final route table can be used to find the shortest route from E to A, you'd find that we have the following reason. So I've written everything down into normal words, and it's everything I basically said. We start at E, which is on the 5th row, and we read across to the A, which is in the first column. We found that there was a D that was over here, and we can therefore say that E to A goes via D. Now, if we consider this D, if we look at the D, which is in the 4th row, and read across to the A, which again is in the 1st column, you'd find that there's a C, and therefore E to D to A goes via C. And if we look at C, which is on the 3rd row, and read across to the A, which is in the 1st column, now you'd find that there's an A. So E to A has this route, E, D, C, A. Okay, so that's all we do for part C. Okay, so now for part D, Mabintu decides to use the distance table to try to find the shortest cycle that passes through each vertex. Starting at D, she applies the nearest neighbour algorithm to find to the final distance table. We have to state the cycle obtained using the nearest neighbour algorithm, and for this question you have to be really careful. You'll notice we have a directed figure network, and because of that, I've just copied it over here. We have to pay particular attention to the way we approach this question. Essentially, because it's a directed network, I mean, if you think about AB, that's 12, whereas BA, that's 15. That's what we mean by it's directed. So the usual thing that you do is look at the columns, but we're not going to do that over here. We will be looking down, we will be looking across the rows instead. Now, we were told that we have to start at D. Now, we don't know if D is optimal or not. All we just know is that we start at D. And if you look across D, you'd find the smallest number to be the 3. So now we can delete off the D row, like so. And if it helps, you can delete the D column as well. Now, this 3 we've circled corresponds to E. So we've started with D. We will now go to E. So let's just write this down. We have D, E. So now that we're at E, the smallest number you'd find is the 7. Okay, so let's just also copy down the numbers as well. So we have 3 plus the 7. And that 7 corresponds to C. So let's delete all of the E row as usual. Let's delete all the E row, and let's also delete the E column, which reminds us that we don't need to look down them again. So now that we're at C, the smallest number corresponds to this 5. Okay, and this 5 takes us up to B. Okay, so we delete all of C, and that tells us that we've finished with C. And you can also delete the column as well to remind you that you don't have to look down it again. And now that we're at C, we go to B, and the smallest one is the 15, which takes us up to A. Okay, so we have C, B, A. So we have 7 plus 3 plus 7 plus the 5 plus the 15. That takes us up to A. So let's just delete all of the B row, and let's also delete the B column, reminding us that we've finished. And now that we're at A, we have to go back to D. And if we go back to D, we still have to go here. So maybe if I box this off, we would have to finish back at D. So we add on another 6. Okay, so that's the first part. This is the second part where we had to, if you go back to the question, that's where we had to state the length of the cycle. So the length of the cycle in miles, don't forget your units, that would be 36 miles. And we don't know if this 36 is optimum or not. Okay, and perhaps if we show that we've finished by deleting all of A as well, just for completeness, that's done. Okay, so now for the third part, which could be more tricky, we have to interpret the cycle in terms of the actual villages visited. Okay, so for this third part of the question, we would have to make use of the this table over here, the root table. Now, D to E, can we do that? If you also go back to the diagram as well, you'd have to switch between the diagram as well. D to E, we can't go any smaller than that. That's fine. Okay, so DE, that's fine. And now that we're at E, we have to go to C. And if you look over here, we're at E, we want to end up at C, and you'll notice that there's a D here instead. So we look down the D, and then we want to go from D to C, and then that has a C in it. So to go from E to C, we'd have to go via D. So we have D, E, D, C. So now that we're at C, we want to go to B. Can we do that? Yes, we can. C to B, that's fine. That's fine. And then can we go from B to A? So B to A, there's an A there, that's fine. Now A to D, we don't know what goes over here. Now you can work your way through it, all iterations, but it's quicker if you look over here. We want to go from A to D. Now A to D, if you look at the diagram, we can do that, but we can also go via E as well, which is shorter. We have the 3 plus the 3, which is 6, and that's smaller than the 18. So it would make sense for us to go from A to D via E. So this is our adjusted route. And for the fourth part, we have to prove that Mabintu's cycle is not optimal. Okay. So we've I've just copied out the table again, just copied and pasted it. Now we want to find a better route than this 36 miles. So we can, the way we can approach this is to, if I get a different colour, the way we can approach this is do the exact same thing. We were told before that we have to start at D. Well, in reality we can start anywhere we want. For example, we can start here at A. Now, if you look across A, the smallest number corresponds to the E. Okay? So we have A, E. So let's delete all of the A row, and let's delete all of the A column. That takes us to E, so we label E with the number 2. And if we look across E, the next smallest number, that's D. So we have D over here. So that takes us up to number 3. And let's delete all of E, indicating we've completed that. Okay, let's just draw straight lines. So let's just put a line through all this. And let's also cross out the column as well. So now that we're at D, if you look across, the next smallest one, that would be C, which takes us to the 4. So we have D to C, so that takes us to the C. So let's delete all of the D row, and let's delete all of the D column. Now we're at C, we can finish off here to B. So let's delete all the C row and the C column, like so. And then now that we're at B, we want to go back to A. That would be this 15 over here. So let's just box that off. So then we have the B to A as shown. And in terms of the length of this, we have A to E, which is 3. Sorry, A to E, which is 3. And then we have E to D, so start at E, finish at D, that's again 3. And then D to C, that would be the 4. And then D to C, so D to C, that's done. And then C to B, that would be the 5. And then the one we finish with is B to A, which is the 15. Now this over here comes to 30 miles. Okay. Now, if you go back to the question somewhere, we were told that with his cycle he started at D, and we have to prove that that's not optimal. And the reason it's not optimal, with his we got 36. Now, this 30 miles is obviously less than the 36 miles. And therefore we can conclude that the route found in part D, I, is not optimal. Okay? And that's how we've shown it. We've just found a different example to show that. Question number 3, examiner report wise. For part A and B, that was quite straightforward. That was using Floyd's algorithm. Many seemed to be happy with this topic, which is quite good. For part A, many were able to find the initial distance and route tables correctly, which is good. A lot of people used the method displayed in the textbook, but those who used alternative approaches also gained equal credit. So A and B were done quite well. There were slight mistakes made, which you can read about. For part C and D, those were a bit more challenging. In terms of part C, many lost marks, though, as they were not clear about how to use the tables. Many did not mention rows and columns specifically, which lost the first 2 marks in this part. So if you look at what I did, so when we talk about E, you have to be specific which row you're talking about, and when we talk about A, you have to be specific which column you're talking about. That's quite important. Also, the second dependent B mark was especially rarely scored, as many candidates did not fully consider the route from D to A. Meanwhile, many candidates who lost these first 2 B marks still earned the third for a correct route EDCA. Candidates should be aware of the level of detail required for a question that requires them to explain a method. Part D, that was quite challenging. If I actually show you my solution to part D, many candidates failed to appreciate that the standard method of applying the nearest neighbour method on a table with undirected arcs will not apply in the same way with directed arcs, so incorrectly stated the nearest neighbour route. I was one of those when I initially did this paper. I was looking at the columns first instead of the rows. So that's quite an important advice. Look at the rows before the columns. Get into that habit. And because they were unfamiliar with that, the other parts of the questions were wrong. For the third and fourth part of part D, that proved to be particularly challenging, with very few candidates realising that the third part was realising the actual route, that the third part was requesting the actual route used, and the fourth part required candidates to find a shorter cycle. In general, proof that a solution to any decision maths problem is non-optimal only requires a counter-example. In other words, a better solution. And that's all you have to do for the fourth part, just find a better solution. Okay, so now for question number 4, the network in figure 3 shows the activities that need to be undertaken to complete a project. Each activity is represented by an arc, and the duration of the activity in days is shown in brackets. The early event times and late event times are to be shown at each vertex, and one late event time has been completed for you, that's shown here. The total float of activity H is 7. I think if we add that in a different colour, that would help. And for part A, we have to explain with detailed reasoning why x is equal to 11. Well, first of all, you have to know the definition of total float. So we've got a copy of the diagram over here. X is 11. We might use this in a later part of the question, but the definition of total float, that's given as the latest finish time, which is the bottom box, minus the duration, which is shown next to the activity, minus the earliest start time, which is shown on the top box. Now, we were told in the question that activity H has a total float of 7 days. So we have 7 over here. And this is equal to the latest finish time, that's 25, minus the duration, we were told that was x, and that's shown here, and the earliest start time, well, that would be over here, where we have 7, because the earliest start time at the end of activity C is 7, and that's because no other activity leads to this event apart from C. So we subtract 7, and I think it would help if we just write that down. So we know that the earliest start time at the end of activity is 7, and that's because no other activity leads to this event, and that's quite clear from the diagram. So when we come to solve for x, we see that x is equal to 11. Okay, now for part B, we have to determine the missing early event times and the late event times, and hence complete diagram 1 in your answer book. Now, I would advise that in the question paper, you try to answer it on the question paper first, and then go to the answer book and then answer it. The reason for that, just in case you make any mistakes, at least in the answer book, you've got a fresh copy. But anyway, let's continue. Now for A, B and C, because no other event leads to these activities, the earliest event times are 8, and here we have to be a bit careful for this box, because going into this box we've got the 8. Remember, we've got a dummy which has a 0 attached to it. Okay, so we've got either the 8 going in, or we've got this 7 going in. Again, remember, we've got a dummy over here, and also a dummy here. And then we've also got the 6 going in. So we compare the 8, the 6, and the 7. The biggest one out of all of these is the 8. Okay? Now, if we take a look at this box over here, well, first of all, 7 plus 10, that would be 17. Okay? And then we've got over here 7 plus the 11, that would be 18. Nothing else goes into H. So we have 18 over here. Now don't forget here, we've got a dummy, so we have a duration of 0. And then 18 plus 0, that's 18. So we have 18 here. What else goes into this box? Well, we have 8 plus the 5, that's 13. And in terms of what else we have, well, 8 plus 11, that would be 19. Nothing else goes in. So here we just have 19. And then 19 plus the 6, that would be 25. The biggest one out of all these is 25, so 25 goes in. Okay, and then here 19 plus 6, that's 25. 25 plus 0, that's 25. And then here we have 25 plus 7, that would be 32. In terms of what else goes in, 4 plus 19, that would be 23. And in terms of what else goes in, 25 plus 7, that would be the 32, we've already added that, and 18 plus 6, that would be 24. The biggest one out of all of these is 32. And then don't forget, we start off with the 0. So we've completed all of the early event times as shown. And if we work backwards, well, here we'll also have a 32, why not? And if we work backwards, well, 32 take away 0, that's just 32, nothing else goes into this box. Here we have 32 take away 6, that would be 26. And if we work backwards here, 32 take away 7, that would be 25. And nothing else goes out. 25 take away 0, that's 25. And therefore the smallest one, that would be this 25 over here. Okay. If we continue to work backwards, 25 take away the 11, that would be 14. Okay, and let's see what else we can take back. 25 take away 10, that would be 15. Okay, so in terms of what else we have, 25 take away the 8, that would be 17. And then 17, well, that's it. 17 take away 0, that's 17. The smallest one out of all these is the 14, so 14 goes in. Let's have a look at this box. 32 take away 4, that would be 28. And 32 take away 6, that would be 26. Okay, and in terms of anything else, 25 take away 6, that would be 19. The smallest one is the 19. Okay, if we continue working backwards, 17 take away 0, that's 17. 25 take away 5, that would be 20. And then we have 19 take away 11, that would be 8. The smallest one out of all of these is the 8. And if we go back to the starting point, 8 take away 8, that would be 0. 17 take away 6, that would be 11. And 14 take away 7, that would be 7. The smallest one is 0. So we've completed our table, our diagram rather. So for part B, let's just write C diagram 1. Okay, hopefully all that makes sense. And now for part C, each activity requires one worker and the project must be completed in the shortest possible time using as few workers as possible. We have to calculate a lower bound for the number of workers needed to complete the project in the shortest possible time. Okay, now first of all you have to know the definition of a lower bound, which is shown here. So the lower bound, that's given by the sum of all the activity times minus the critical time of the project. And for that, if we work in alphabetical order, we've got 8 plus 6 plus 7. Let's just write this down. So we have 8 plus 6 plus 7. So that's A, B and C done. Then we have D, E, F, G. So we have 11, 5, 8 and 10. So we have 11 plus 5 plus 8 plus 10. Okay. So that's that done. So E, F, G. And then we got H, I, J. So we've got 11 plus 6 plus 4. So we have 11 plus 6 plus 4. Okay, so that takes us up to here. And then we've got K, which is 6, and then L, which is 7, and M, which is 6. So we've got 6 plus 7 plus 6. So let's just write that down. We've got 6 plus 7 plus 6. So that's from A to M. And then the critical time of the project. Well, for that, we would have to find the critical path before we do that. So if you look back over here, the critical path, well, we go from A to D, and then from D we go to J. Sorry, no we don't. From D we then go down to this K, and then we go to L. Okay, so the critical time of the project, that would be this 32 over here. So the critical time of the project, that would be 32. So we have 95 over 32, and if we work this out, we have 95 divided by 32, which is 2.96 etc. So we have 2.96 etc. and therefore the lower bound, we want integer numbers, lower bound is 3. Okay. Now for part D, we have to schedule the activities using grid 1 in the answer book. I think before we do that, I think it would be a good idea to work out the floats. And we'll do all them in green. Now the float here for B, 17 take away 6 take away 0, that would be 11. What else do we have? 25 take away 5 take away 8, that would be 12. Yeah, that would be 12. Here we have 25 take away 8 take away 8, that would be 9. Here we have 25 take away 10 take away 7, that would be 8. Here we have 32 take away 6 take away 19, that would be 7. Here we have 32 take away 4 take away 19, which is 9. Here we've got 32 take away 6 take away 18, which is 8. And here 25 take away, sorry, we've already filled that out. That's all the floats shown in green. Obviously A, D, K and L have no float, they're critical activities. Okay, so let's now look to fill in our grid. Right, so I think the first thing to do is start off with A, B and C. Those have durations 8, 6 and 7. So if we start off with A, that has a duration of 8. So let's just box that off. So we have A over here, and then B that has a duration of 6. So that takes us up to here, and C has a duration of 7. So that would take us up to here. Right, let's just fill those out. we have A, B, and C. Okay, now it would be a good idea to fill out the critical activities. So we have D, K, and L. Those have durations 11, 6, and 7. So let's grab a calculator. We have 8 plus 11, which is 19. So D takes us up to 19. Let's just add that on the diagram. So from here we've got we go to 19, okay, and then we've got K, and if you look at the duration of K, that was 6. So 19 plus 6, that would be 25. So 25, that takes us up to here, and then we've got 25 plus 7, that takes us up to the 32. So that takes us up to here. Okay, so we've got A, D, K, and L. Those are our critical activities. Everything else is non-critical, and everything else that's non-critical will show in a different colour. Now let's have a look at the activity. Well, if you look at G and H, those depend on C only. G has a duration of 10, H has a duration of 11. So if we think about G has a duration of 10, so that would take us up to 17 after C. So after C, from here, 17, that takes us up to here. So that over here is activity G. And then we've got H. H has a duration of 11. So 7 plus 11, that would be 18. And that makes complete sense if you think about it. That's our earliest start time. So from C, we can go here and finish off at 11. Okay, and although we found the lower bound to be 3, remember it's just a lower bound, we can have more, you can have more over here. We're not just restricted to 3. So here we have H. Now let's take a look at E. E depends on D finishing. So, sorry, E depends on A finishing, and E has a duration of 5. And the earliest we can, we have to be done by 25 essentially. If we think about E, that has a duration of 5, that would take us up to 13 from A. So if we go back down here, after A, we can go straight to E. So that has a duration of 5, and then we have 13. Okay, and if we think about F, wherever F is, for F we have to be done before 25, and that has a duration of 8. And if you think about this, we're at 13 now, and if we add 8, that'll take us up to 22, and obviously we'll start before the 25, which is the earliest and latest start time and finish time. So we can go to F, which will take us up to 13 plus 8, that's 21. So we can end up at 21 here. Okay, so here we have F. Okay, so we have E and F. Okay, and if we now take a look at I, that's to be done before well, the early event time is 25 and the late event time is 32, so we can finish before 32. And remember, we've got this float as well that we can play around with. So if we say that I starts after F, that'll take us up to 26. So let's just show that. So we've got 26 over here. Okay, so here we have I. So that's I. Let's have a look at J. If we look at J, J, the earliest J can start is after 19. So that's a duration of 4. So let's add that on after G, alright, because the earliest we can start is at 19. So if we add that in, J starts at 19, and that is a duration that will take us up to 23. So let's just show this. So 23 is over here. Okay, so this over here is J. And let's see what else we can do as well. Well, we've only got one left. I think it's M left. M can start after 18. And the latest it can start is 25. But we've got this float. We've got finished before 32. We've finished at 23, so we can include M after J over here, so that'll take us up to 29, I believe. So here we have this taking us up to 29, like so. So here we have M. Okay, so that's everything, and the rest of these boxes where we haven't filled in anything, we'll just fill in with a black box. Okay, so let's just fill this in. Yeah, like so. Okay, so that's our critical path, that's our resource diagram done then. Okay. Question 4, examiner report wise, that was concerned with activity networks. Part A, where we had to explain why x equals 11, very few candidates gave, very few failed to give a detailed reason as to why x equals 11. For the first mark, candidates had to give a correct reason why the total float on activity H was given by 25 minus 7 minus x. So for example, mention that the early event time at the end of activity C is 7, and for the second mark, which is dependent on the first, a reason why the expression 25 minus 7 minus x leads to the given answer. Far too many candidates gave no reasoning at all and simply wrote down the equation 25 minus 7 minus x equals 7 and then stated x equals 11. So note in the question it said explain with detailed reasoning, so make sure that you give a detailed answer. Part B was done quite well as part C, where you had to fill in the network and then find the lower bound. For part D, that was concerned with scheduling activities. A lot of people used their lower bound, which was incorrect, and that's mentioned here. However, a significant proportion of candidates tried to construct a schedule with only 3 workers, possibly due to their answer for part C, therefore scoring only 1 mark and completely disregarding the significance of the immediately preceding activities. Of those candidates who did have 4 workers in their schedule, a pleasing number were correct, though errors were sometimes seen in either the duration, time interval or IPA for one or more activities, it was pleasing to note that the cascade charts were rarely seen. Okay, so for question number 5, we have to draw the activity network described in the precedence table above using activity on arc. Your activity network must contain only the minimum number of dummies. Now, I think it would be a good idea to begin by stating the definitions of a dummy. We use a dummy when we have at most one activity between two events, and we have two or more activities that depend on a common activity finishing, but also depend on activities that are not common in finishing. Okay, so with that, let's begin. Now we've got A, B and C which depend on nothing. So they start off from our source. Now I recommend just quickly sketching everything first and then copying everything out neatly. So that's A, B and C done. Tick as you go along. You've got D which depends on A, and you've got also G which depends on A. Okay, so G goes over here. And you've got E which depends on C, so we've got E over here. And you've got F which depends on B, C and D. So we've got B, C and D finishing right. If I swap the D and the G round, so we have G over here and D over here, then we know that F depends on B, C and D finishing. Now you have to be a bit careful over here. Here we require a dummy, so make sure that you show the dummy. So that's F done, and H also depends on B, C and D. So we've got H coming out over here. Okay. Now if you look at I, that depends on B, C, D and G finishing. So we've got B, C, D finishing, and we've also got G finishing as well. So what activity was that again? That was I. So we have to have a dummy here and then I coming out like so. Okay, and remember we require a dummy because we can have at most only one activity between two events, and we see that we have two or more activities which have a common activity finishing but also depend on activities that are not common in finishing. So that's I done, and then we've got J done as well, like that. Okay, like so. And then we've got K which depends on E and H. So E and H finishing, then we've got K coming out like so. And then if you put a sink, you've obviously got K going to the sink, you've got F going to the sink, and we can't have this situation going on, so of course we'll need a dummy. So if we have I over here, then we can convert this thing over here to a dummy like so. So if I show that, we've got a dummy here, and that's our completed diagram. Now our next step would be to draw this out neatly, which I will do right now. So what we have over here then is our completed activity network. Okay, we've got A, B and C starting off from the source, and going to the sink we've got I, J, K and F. Okay, now for part B, given that all the activities shown in the precedence table have the same duration, we have to state the critical path of the network. Now, even though it's only worth 1 mark, I would recommend that you all draw out the diagram again, this time with the boxes showing the early times and the late times, okay? So perhaps if we write this down, if you think about this in terms of numbers, it would make your life a bit easier. So let's just write this down. Let's write down example with numbers, okay? So we have here an example with numbers. And if you do that, it will make a lot more sense. Now, if we say that they all have a duration of 5, for example, okay, let's just fill all these activities in with a 5. Then obviously here we start off with 0. Going into here we've got the 5, and going here we've got 5. Here we can either have the 5 from the B, or we could have this 5 plus this 5, which is 10. So we have 10 going over here. And for this one, we've got 5 plus 5, which is 10. Let's just copy and paste another one of these. I think I forgot one out. Let's move this here. And in this one, we've also got a 10 because we've got a 0 over here. Let's just add the 0 in. We've got 0 here, here, and here. And for this one, we can have 10 plus 5, which is 15, or we could have the 5 plus 5, which is 10. 15 is a bigger one, so 15 goes here. And for this one, the biggest one we can have is the 15 plus the 5, which is 20. Okay, and going backwards here, we've got 20. Here we've got 15. Here we've got 10. Here we've got 15 going back. Here we've got 15. And here we've got 5. Here we've got 10. And here we've got 0. Okay, so it's just a standard sort of problem with this. And when we come to talk about the critical path, we see the ones with 0 float. We have A, D, H, and then K. Okay, so let's just write down that critical path. The critical path that would be A, D, H, and K. Okay. Question 5, examiner report wise, that's when we had to draw an activity network. A lot of people are beginning to understand this sort of question, which is good. I always like to give the definition of a dummy before I attempt these questions, just to remind myself when I will use a dummy. Now, we've got some interesting comments over here. Some scripts lacked a sync node at the end, and a small number did not have a single source node. Some of the diagrams and labels were challenging to read, especially when they were very small and or drawn with lines that crossed over them. So I'd say draw the network first and then add the the activities. Some candidates were unsure about the placement of their dummies, putting them in anywhere so that the precedence was guaranteed. A small number of candidates put activity on node, and some failed to check that they had all the activities present, with activity K being the activity that was missing most often. We've got further comments. Whilst most candidates now seem to be aware of the importance of arrows on dummies, there are still some candidates who make the costly mistake of not having arrows on their dummies. This makes it impossible to determine the preceding activities for F, H, I, and J and K, and ultimately lost 3 marks. So that's on about here. For part B, where we have to where we were given that all activities have the same duration and we had to find the critical path, very few candidates failed to give the correct answer. I'd say if you put an example with numbers, that makes life a bit easier for yourself, and then you can quite easily spot the critical path. For question number 6, a linear programming problem in X, Y and Z is described as follows. We have to maximize P equals 2x plus 2y minus z, subject to 3x plus y plus 2z being less than or equal to 30, x minus y plus z being greater or equal than 80, 4y plus 2z being greater or equal to 15, and x, y and z all being greater than 0. For part A, we have to explain why the simplex algorithm cannot be used to solve this linear programming problem. Well, we've got the following reason. It's quite a straightforward reason. The simplex algorithm can only be applied when the non-negativity constraints are less than or equals to. Now for part B, we have to set up the initial tableau for solving this linear programming problem using the big M method. Now, just as a reminder, in the big M method, M is used to represent an arbitrary large number, and this guarantees that a term such as M minus 100 will be positive, and a term such as something like 75 minus 0.5 M will be negative. Okay? So let's begin. We've got this 3x plus y plus 2z being less than or equal to 30. Okay, let's begin with that. We've got 3x plus y plus 2z being less than or equal to 30. We've also got x minus y plus z being x minus y plus z being greater or equal to 8, and we've also got 4y plus 2z being greater or equal to 15. Okay, so first of all, we have to write the inequalities as equations using slack, surplus and artificial variables. So doing that, for this equation here, and I'll just rule off quickly. Just quickly rule off. For this first equation, we've got 3x plus y plus 2z plus s1 equals 30. Okay, let's just move this up a bit. Equals 30. For this other equation, we've got x minus y plus z, and then we have to be a bit more careful over here. We have minus s2 plus a1, and this is equal to 8. And similar thing over here, we have 4y plus 2z minus s3 plus a2 equals 15. Okay, and having written those down, if we rule off again, for these equations over here, we can rewrite those in terms of a1, and the reason we do that will become clear soon. So if we rearrange for a1, we see that a1 is equal to 8 minus x plus y minus z plus s2, and if we arrange for a2, we see that a2 is equal to 15 minus 4y minus 2z plus s3. Okay, now if we go back to our p function, we need to rewrite this. So in terms of the p function, we have the following. We know that p is equal to 2x plus 2y minus z. Okay, and we wish to rewrite this now. Because m is large and positive, maximizing this, if we modify this objective function, because m is large and positive, maximizing the modified objective function will automatically push a1 and a2 to 0. That's what we mean by that is, when we modify this objective function, we subtract off m lots of a1 plus a2. So from here, again, if we rule off, if we rewrite this, we have p equals 2x plus 2y minus z minus m lots of a1 plus a2. Okay, and with a bit of algebra, if we call this equation 1, this equation 2, and this equation 3, if we add together equation 1 and 2, that will get us a1 plus a2. So that's why I rearranged for a1 and a2, because with our modified objective function we were going to subtract off m lots of a1 plus a2. So with that, if we add equation 1 and equation 2 together, we see that a1 plus a2 is equal to 23 minus x minus 3y minus 3z plus s2 plus s3. We'll call this equation 4. And now if we substitute in equation 4 into equation 3, we have the following. We have p equals 2x plus 2y minus z minus m lots of 23 minus x minus 3y minus 3z plus s2 plus s3. And we now wish to rearrange this equation, and if we call this equation 5, if we rearrange equation 5, first of all expanding the brackets, we see that we have p equals 2x plus 2y minus z minus 23m plus mx plus 3my plus 3mz minus m s2 minus m s3 equals 6. And if we therefore rearrange this equation, we have p minus 2 plus m x minus 2 plus 3m y minus 1 plus 3m z plus m s2 plus m s3 equals minus 23 m. Okay, and now, having found out what p is, and we've also got these other equations, we can now set up our initial table. Okay, so we'll do that now. Okay, so looking at this equation in red and the two equations in blue over here. And then this bottom equation here, we can therefore conclude that we have this table over here. We can fill everything in. For the basic variables, we have S1, A1 and A2. Okay, and the way we look at this is, for this equation we have 3, 1, 2, 1 and then 30. Okay, that's filled in nicely for us. So we have 3, 1, 2, 1, and here we have zeros. And next, for these other equations, these other two, in red, we have here 1, minus 1, 1, 0, minus 1, 0, 1, 0, and the 8. And then here we have, if you look at this other red equation, that's got no x's in, so we have 0, 4, 2, 0, 0, minus 1, 0, 1, 15. And then finally, using this equation, we have minus 2 plus m minus 2 plus 3m minus 3m minus 1, 0, m, 0, 0, and minus 23 m. Okay. For part C, after a first iteration of the big M method, we've got this table over here. We have to state the value of each variable after the first iteration. That's quite straightforward. I've written it down somewhere here. S1 is equal to 26.25, A1 is equal to 11.75, Y is equal to 3.75, X, Z, S2, S3 and A2 are all equal to 0. And you can see that from this table over here. Now for part D, we have to explain why the solution given in the first iteration is not feasible. Well, if you look at this A1, which is 11.75, we want A1 to be 0 for a feasible solution. So we've got the reason over here. The solution after the first iteration is not feasible because A1, which is 11.75, is an artificial variable which must be 0 in a feasible solution. And now for part E, taking the most negative entry in the profit row to indicate the pivot column, we have to obtain the most efficient pivot for a second iteration. You must give reasons for your answer. Well, if you look along this P row, the most negative value in this objective row, that would be the 2 minus 1.5m. And therefore, the pivot is in the Z value. Now, if we work out our values of theta, let's work these out. 26.25 divided by 1.5, this is 17.5. 11.75 divided by 1.5, that is 7.83, etc. And then 3.75 divided by the 0.5, that's 7.5. Okay. So what was that? So that's 7.5. And therefore, because this is the most negative entry, our pivot is this 0.5? Okay, so let's just put that down into some sort of words. So the most negative entry in the objective row is the 2 minus the 1.5m. So the pivot is a value from the z column, and the 0.5 in the y-axis is the pivot because the 3.75 over 0.5 is less than both the 26.25 over 1.5 and the 11.75 over 1.5. And we discussed that over here. Okay, so that's question 6 done. Question 6, examiner report wise, this was concerning linear programming with the big M method. A lot of people for part A, where we had to explain why the simplex algorithm cannot be used to solve this linear programming problem. Many gave a correct response, but there were some incorrect responses which included statements such as the problem has 3 variables or it needs artificial variables. Part B, where we had to set up the initial tableau for solving this linear programming problem, a lot of candidates made a good attempt, but there were certain errors such as sign errors with the second and third constants, adding surplus and variables and subtracting artificial variables. A significant number of candidates made the mistakes with their objective function, and you can read about that in the examiner reports. There were some candidates who left some cells blank, and some made an incorrect simplification of the objective function, and therefore this final row was incorrect. Part C, where we had to state the value after each iteration, that was done quite well, but there were some who failed to state the value of adding of the 5 zero variables, and a small number of candidates either omitted one of these or added an extra one, sometimes duplicating one of the non-zero variables. For part D, where we had to explain why the first iteration was not feasible, the majority failed to give a correct reason, with many stating that there were negative values in the objective row, or making a general comment such as not all the artificial variables are 0, or the sum of the artificial variables is not 0. Other incorrect statements include A has a value, and then we've got some correct responses that were given. For part D, where we had to talk about our pivots, there were a lot of candidates who were unsure about the pivots, and I think we discussed the pivots here somewhere. But the main reason why people were struggling was got this answer wrong was because they did not explain properly. Okay, so for question number 7, a shop sells 2 types of watch, analog watches and digital watches. The shop manager knows that each month she should order at least 60 watches in total. In addition, at most 80% of the watches she orders must be digital. Let X be the number of analog watches ordered and let Y be the number of digital watches ordered. For part A, we have to write down inequalities in terms of X and Y to model these constraints. Well, that's quite straightforward. For the first one, if we've got at least 60 watches in total, that suggests to us that X plus Y is greater or equal than 60. Okay, and if we have 80% of the watches being digital, remember Y is digital, then we have Y is less than or equal to 4/5, which is 80%, lots of X plus Y. Okay, which we can rewrite as, if I expand out, we have 5Y being less than or equal to 4X plus 4Y, from which we see Y is less than or equal to 4X. So that's part A done. And now for part B, we've got 2 further constraints. Let's just quickly copy those down. We've got Y plus 3X being greater or equal to 140. And let's just write that out neatly. And what else do we have? We've got 4y plus x being greater or equal to 80. Okay, so with that we have to represent all these constraints on diagram 1 in the answer book, and then hence determine and label the feasible region R. Okay, well, x plus y being greater or equal to 60, we'll show that in red. So if we show that, let's get a straight line. We've got this point joining to this point. So this over here is, if we label this, this is the x plus y equaling 60. For the next one, we've got y being less than or equal to 4x. So if we plot this in blue, so we have something looking like this. So we have 1, 2, 3, 4. So that should go over here. So we have 1, 2, 3, 4. And then the other point goes down over here. Okay, so that then is the other equation of y equals 4x. Let's just label that as well. So here we have y equals 4x shown here. The next one is y plus 3x equals 140. So when x is 0, y is 140. So let's just show that. So when x is 0, y is 140. And then when if x is, I don't know, 30, then we have 3 times by 30. Well, let's work this out. We have 140 minus 3 times by 30, which is 50. So when x is 30, y is 50. So when x is 40, y is 20. So when x equals 40, y is equal to 20. And when x is 0, y is 140. Okay, so let's just join these up. So that's the first one, and then continuing this down, we have that line shown over here in green. So this over here then is y plus 3x equaling 140. Okay, hopefully that makes sense. So when x is equal to 40, y is equal to 20, yeah, that's fine. And finally, for the last one, which we'll do in orange, 4y plus x is greater or equal than 80. So when x is 0, y is 20, and when y is 0, x is equal to 80. So that goes over there like so. So what we have over here then is our fourth equation in orange, which is 4y plus x equals 80. Okay, so having plotted all those, we now have to show our feasible region. So we have x plus y being greater than 60, y being less than or equal to 4x, y plus 3x being greater than 140 and for y plus x being greater than 80, our feasible region therefore is all over here. If I can show this properly, that would be good. So we have something going over here. So that's that one, and then if we move this down, so here I'm just showing our feasible region, like so. Okay, so here we have our feasible region R. And don't forget, I think there were further inequalities. X plus y must also be greater than 0. Okay, so x and y must be both greater or equal to 0. So let's just finish off showing that like so. Okay, so yeah, that's that complete. So that's part B complete. Now for part C, the cost to the shop of ordering an analog watch is 5 times the cost of ordering a digital watch. The shop manager wishes to minimize the total cost. We have to determine the number of each type of watch the shop manager should order. You should make a method clear. Okay, so well, over here we have to show the points of intersection. So we've got this point of 80, 0. Well, I'll be a bit more clear. I think one of the best ways to approach this question is to first of all determine the points of intersection first, and then sub those into your objective function. Now here we have the point 80, 0, and then here we can figure out this point by solving this x plus y equals 60 simultaneously with 4y plus x equals 80. So let's do that on our calculator. It'll be quicker on the calculator. So we have a simultaneous equation. We have x plus y equals 60. Oh, damn. Sorry, we have a simultaneous equation. So we have x plus y equals 60. Solving that simultaneously with 4y plus x equals 80. We see here we have a intersection point of 160 over 3 and 20 over 3. So here we have 160 over 3 and 20 over 3. Next, let's solve the red line with the line over here. So we have x plus y equals 60 solved simultaneously with this 3x plus y equals 140. We get x equals 40 over here, and y is equal to 20. So that's another point of intersection. And finally, we've got this one over here, the blue one with the green one. So we've got minus 4x plus y equals 0, and we've also got 3x plus y equals 140. So we see that x is 20, y is 80. So here we have x equals 20, y equals 80. Okay? And don't forget, here is our feasible region R. Okay. So having done all that, I think now we have to, I think the question said something about minimizing. So let's just go back. Yeah, the shop manager wishes to minimize the total cost. Okay, so for that we need to substitute these points into our objective function. Okay, so our objective function will be of the form p equals k lots of, and if you go back to the question actually, we know that the cost to the shop of ordering an analog watch is 5 times the cost of ordering a digital watch. So our objective function would be of the form if we think about this, our objective function will be of the form 5x plus y, okay? Because the cost of an analog is 5 times that of a digital, okay? So having said that, let's think about this. Okay, so yeah, that seems fine. Obviously k is a constant. Now if we substitute each of these points in, so if we substitute in the 2080, the value we come out with, p is equal to 5 times by 20 plus 80, which is 180. So we have k lots of 5 times by 20 plus 80, which is 180k. Okay, the next one we've got is 4020. So if we substitute that point in, we have p equals k lots of 5 times by 40 plus 20. So we have 5 times by 40 plus 20, that's 220. Okay. The next point we've got is 160 over 3 and 20 over 3. So we have 160 over 3 and 20 over 3. So we have p equals k lots of 5 times by 160 over 3 plus 20 over 3. And if we work this out, we have 5 times by 160 over 3 plus 20 over 3, which is 820 over 3, which is the same as 273.33, etc. Okay, and remember this k is just a constant. Okay, let's just write that down. K is a constant. And the last point we've got is the AT0. So if we substitute that in, so the AT0, we have p equals k lots of 5 times by 80 plus 0. So it turns out we get 400k. Obviously the smallest one is the 180k, and therefore we can conclude from here that we need 20 analog watches and 80 digital watches. Okay. So that's part C done. And now for part D, given that the minimum total cost of ordering the watches is 4455, we have to determine the cost of ordering one analog watch and the cost of ordering one digital watch. Okay, so well, we know that we need 20 analog and 80 digital, and we know that the minimum is 4455. So that's one equation we can use. 20A plus 80D equals 4455. And the other equation which we can use, we know that the cost of an analog is 5 times that of a digital. And if we solve these simultaneously, so if I call this equation 1 and 2, so if we now solve equation 1 and equation 2 simultaneously, so let's just grab our calculator. We have 20A, so we have 20A plus 80D, that's equal to 4455, and then we've got A minus 5D equals 0. We see that A is equal to 123.75 and D is equal to 24.75. okay, and therefore we can conclude that in analog watch costs £123.75, and a digital watch costs £24.75. okay. Okay, so now for question number 7. This was concerning linear programming again. For part A, where we had to write down the inequalities in terms of x and y, those that talked about, well, the one where we have the at least 60% in total, that was done pretty well. Where it was talking about the at most 80% of watches, some candidates did not really know what they were doing. It says over here in the examiner reports, this was either dealt with very little, with very well by candidates, or not attempted at all, with a minority giving either the inequality or the variable transposed. I thought it was quite straightforward personally. And then for part B, where we're given the extra 2 constraints and then we had to draw the inequalities on a diagram. I mean, drawing inequalities is nothing more difficult than GCSE personally, I think. But anyway, there's a couple of things which are mentioned over here. Most candidates were able to draw the required lines correctly in B, although some were unable to draw the line sufficiently accurately. Some drew lines without a ruler or sufficiently long enough. As stated in previous reports on the legacy specification, the following general principle should always be adopted by candidates. Lines should always be drawn with which cover the entire graph paper supplied in the answer book, and therefore lines with negative gradient should always be drawn from axis to axis. So if you look at, if you go to my solution, wherever I put that, with a negative gradient like the orange, the green and the red ones, we have to draw these axis to axis. So from this axis to this axis. The rationale behind this is that until all the lines are drawn and shaded accordingly, it is unclear which lines or part of lines will define the boundary of the feasible region. If candidates only draw the line segments as they believe define the boundary of the feasible region, then examiners are unaware of the order in which the lines were drawn, and therefore it is unclear to examiners why some parts of the lines have been omitted. Furthermore, a significant number of candidates were unable to select or even label the correct feasible region. I thought it was quite easy if you label everything correctly. That was talking about an objective function. There were two methods. You can either use the ruler test or use the intersection points. I think using the intersection points was a bit easier. But anyway, let's take a look at what the examiner report said. Reciprocal gradient objective lines were shown by a significant number, which of course usually meant choosing the wrong vertex. Where point testing was used, there were a surprisingly large number of calculation errors. When vertices were read off the graph, they were rarely checked algebraically to confirm if they were correct. So I think what people did was, if I go back to this graph, like over here where they were finding the intersection point, I think they were trying to read off just from the graph, and that's actually quite hard to do in my opinion. So if you look at it algebraically, it's a bit easier to find the exact point. And even then, look, I can zoom in nice and big on a computer. I can zoom in to sort of this level of accuracy, so I can sort of see that third in the X direction, and then it's easier like that to see. But whereas if you do it on actual pen and paper, it becomes a bit more difficult to actually find the exact point, which is why solving them simultaneously is a better option. And even then, when I did solve them simultaneously, I just did it on a calculator, which is a lot easier. So that's that point talked about. So that's what's said over here. If candidates are to use point testing, it would be advisable in most cases to find the intersection points using simultaneous equations rather than reading off the graph. Some candidates did not show a method at all, and hence gain no marks in this part. A small number of candidates stated the correct values for X and Y, but failed to give these in terms of number of watches of the manager should order, and so failed to gain the final accuracy mark in part C. So in terms of part C, where we had to determine the number of each type of watch the manager should order, it was often the case that this part of the question was left blank. Those candidates who did attempt this part usually scored at most 2 marks, as they had failed to find the correct optimum point in part C. Many candidates in part D attempted to combine the two relationships, which involved the total cost of watches and the relative cost of the two types of watches in one step. While many candidates completed this successfully, a significant number made errors confusing analog equals 5 digital with digital equals 5 analog. For part D, where we were given the minimum and then we had to find out the cost, several candidates in part D stated an incorrect equation that related their objective function with the total cost of the watches. This meant that the equation analog plus 5 digital equals 4455 was often seen by examiners. And finally, several candidates made no use of the total cost of the watches in any part of their solution.